It was a fortress designed to withstand the apocalypse. K-141 Kursk Oscar II class submarine displaced over 19,000 tons submerged. Its revolutionary double-hull construction, with an outer hull of high nickel, low magnetic steel, separated by a massive 2-meter gap from its 5-centimeter thick inner pressure hull, was engineered to shrug off torpedo impacts and even survive the overpressure of a nearby nuclear detonation. It was, by every metric, a titan, an unsinkable city of steel. And yet, on August 12, 2000, in the Barents Sea, this indestructible machine was annihilated, not by an enemy destroyer or a hunter-killer submarine, but by a catastrophic event inside its own torpedo room. The threat wasn't external. It was locked in one of its own weapons. How could a single piece of ordnance, a practiced torpedo, breach a vessel built to fight World War III? This is the story of the Kursk and the engineering flaw that sealed its fate. We will dissect how it was designed and why it failed. To understand the Kursk, we must first understand the strategic problem it was built to solve. By the 1970s, the Cold War at sea was dominated by one machine, the American supercarrier. These billion-dollar, 90,000-ton behemoths were floating air bases, protected by concentric rings of destroyers, cruisers, and hunter-killer submarines. They weren't just ships. They were mobile pieces of sovereign territory, capable of projecting overwhelming air power, including tactical nuclear strikes against the Soviet homeland. For the Soviet Navy, this was an existential threat. They could not compete carrier for carrier. The cost was prohibitive, and the technological gap in carrier operations was too wide. The solution was asymmetric. If you cannot kill the king's guards, you build a weapon that can kill the king in one shot. This doctrine created a new class of warship, the podvodnaya lodka atomnaya raketami krylati, or submarine, nuclear-powered, with cruise missiles. Its NATO designation was SSGN. The Kursk was a Project 949A Anti, known in the West as the Oscar II class. These were not subtle hunter-killers designed for quiet patrols. They were brawlers, underwater battleships built for a single brutal purpose: to find an American carrier battle group, stalk it from the deep, and then unleash an overwhelming salvo of anti-ship missiles. This singular mission defined every aspect of its design. It needed to be fast enough to keep pace, quiet enough to evade the S-3 Viking and P-3 Orion patrol aircraft, and tough enough to absorb a torpedo hit and keep fighting. Above all, it needed to carry a weapon capable of killing a supercarrier. The resulting design was a Goliath, the largest attack submarine ever built, a 155-meter-long Titan dedicated to one of the most difficult missions in naval warfare. The Oscar II was less a submarine and more a submerged battlecruiser. Its sheer scale was staggering. To grasp its engineering, we have to digitally build it, layer by layer. The Kursk's most defining feature was its revolutionary survivability. When we peel back the 8.5mm thick, high-nickel steel outer hull in this cross-section, we can see the true innovation. There is a massive 2-meter gap in some places, even wider before we reach the inner pressure hull. This inner hull was the submarine itself, a 5-centimeter thick citadel of steel that protected the crew and reactor. This double hull design served two purposes. First, it provided an enormous buoyancy reserve of over 30%. In theory, the Kursk could remain afloat even with an entire compartment and its adjacent ballast tank completely flooded. Second, the outer hull was a sacrificial layer designed to detonate incoming torpedoes before they could ever reach the pressure hull. The space between was a standoff buffer. The 130-man crew was further protected inside 9 watertight compartments, separated by heavy-gauge bulkheads. But this fortress was built to launch a devastating offensive. Housed between the two hulls, we find the Kursk's primary weapon. Here, angled at 40 degrees, are 24 launch tubes for the P-700 Granite anti-ship missile. NATO codename Shipwreck. These were not simple weapons. Each Granite was a 10-meter-long, 7,000-kilogram monster, a sea-skimming cruise missile capable of Mach 2.5. They were designed to be fired in a wolf-pack salvo. One missile would fly high, using its radar to designate targets for the others, which screamed towards the enemy just meters above the waves. A single Granite warhead could cripple a destroyer. A full salvo was considered sufficient to saturate the Aegis defenses of a supercarrier and score multiple mission-killing hits. This was the Kursk's main battery, but for our investigation, we must move forward to the bow. To Compartment 1, the torpedo room. This room carried a mixed load of 24 torpedoes and missiles, and it was here that the Kursk carried its fatal flaw. Among the modern battery-powered torpedoes was an older, larger, and far more powerful weapon. The Type 65-76, nicknamed the Kit, or Whale. This was a 650mm wake-homing torpedo, a 10-meter-long brute designed not to hit a carrier, but to detonate in the turbulent water of its wake, snapping the vessel's keel. To achieve the speed and range needed for this, the Type 65 did not use conventional fuel. Our analysis of the torpedo's internal schematic reveals its power source: a turbine engine propelled by the volatile, explosive decomposition of high-test peroxide, or HTP. HTP is a clear, seemingly harmless liquid, but at 85% to 98% concentration, it is a chemical monster. It is one of the most powerful oxidizers known to engineering, second only to liquid oxygen. When HTP touches a catalyst or impurities like rust, brass, or organic matter, it instantly uncorks, decomposing into superheated steam and pure oxygen at over 500 degrees Celsius. This is precisely what made it a miracle propellant in the 1950s. But it was also legendarily unstable, corrosive, and prone to spontaneous explosion. By the year 2000, most Western navies, including the British Royal Navy, who lost the HMS Sidon to an HTP torpedo, had abandoned it as dangerously unsafe. The Russian Navy, however, continued to use it. The Kursk, this 21st century super submarine, was carrying a 1950s-era chemical liability. The safety of this entire system depended on the flawless integrity of the torpedo's fuel tank, specifically its internal welds. Our forensic reconstruction of the Kursk's final moments begins at 11:28 a.m. local time on August 12, 2000. The Kursk is at periscope depth, running drills in the Barents Sea. In Compartment 1, the crew is preparing to load a 650mm Type 65 practice torpedo, filled with HTP propellant, but carrying an inert warhead, into a tube. This is where the failure begins. We must trace it to a microscopic level, deep inside the torpedo's propellant tank. A faulty weld, a tiny, imperfect seam in the metal, finally gives way under pressure. High-test peroxide, the 85% concentration miracle fuel, begins to seep out. This is not a passive leak. The moment the HTP trickles past the weld, it comes into contact with impurities inside the torpedo casing, microscopic particles of rust, a smear of grease, or perhaps the copper and brass of the casing components themselves. For HTP, this contact is a catalyst. At 11:28 and 26 seconds, the chemical reaction is instantaneous and violent. The HTP uncorks. It begins to decompose at a catastrophic rate, flashing into superheated steam and pure pressurized oxygen at over 500 degrees Celsius. The internal pressure of the torpedo casing spikes. This is not a warhead detonation. This is a chemical explosion. Our analysis of the pressure hull's acoustic signature shows what happened next. The practice torpedo ruptures. Its entire 1,000-kilogram load of HTP propellant flashes to vapor, expanding at nearly 5,000 times its liquid volume. This initial blast is equivalent to 100 to 250 kilograms of TNT. It is more than enough. The explosion atomizes the forward bulkhead of Compartment 1. It slams into the aft bulkhead, a 2-ton circular steel door designed to protect the rest of the submarine, and rips it from its hinges, turning it into a projectile. A 2,000 degrees Celsius fireball, supercharged by the pure oxygen released by the HTP, erupts from Compartment 1 and surges down the passageway into Compartment 2, the command and control center. The 7 men in the torpedo room are instantly vaporized. The men in the command center, including the ship's captain, are killed seconds later by the concussive force and the incinerating flash fire. The Kursk is now a dead ship. Its brain is destroyed. It is mortally wounded, blind, and flooding, beginning its final plunge to the seafloor, 108 meters below. But the catastrophe is not over. This was only the first explosion. Back in Compartment 1, a furious fire now rages, fed by the oxygen-rich environment. The compartment is flooding with seawater, but the inferno is hot enough to flash it to steam. And this raging fire begins to cook off the remaining 23 weapons. For 135 seconds, the Kursk falls through the water. Then, the fire finds the combat-ready warheads. At 11:30 and 41 seconds, the seismic sensors on the Norwegian coast detect a second event. This is not a chemical reaction. This is a mass detonation. Our analysis of the wreckage indicates that at least 5, and perhaps as many as 7, combat-ready torpedo warheads exploded simultaneously. The force is apocalyptic, registering 4.2 on the Richter scale. This blast is equivalent to over 3 tons of TNT. It rips the Kursk apart. The indestructible double hull, the 2-meter standoff gap, the reinforced bulkheads, they are rendered meaningless. The entire bow of the submarine, from Compartment 1 through Compartment 3, is vaporized, reduced to a jagged field of shredded steel. The sea rushes in, and the 19,000-ton Titan strikes the seabed, its fate sealed. So how did an unsinkable fortress, built to survive a nuclear war, get annihilated by its own practice torpedo? The simple answer is a faulty weld. But our forensic analysis concludes this is not the true tragic flaw. A single faulty weld is a component failure. The Kursk's demise was a systemic failure. The real flaw was the institutional gamble on high-test peroxide. When we examine the engineering doctrine, we are forced to ask why the Russian Navy, unlike its Western counterparts, continued to use a propellant known to be catastrophically volatile. The answer, as always, is performance. The HTP-fueled Type 65 torpedo offered superior speed and range, a weapon ideally suited to its carrier-killer mission. The Russian Admiralty accepted the risk. They bet that meticulous maintenance and handling procedures could tame the chemical's violent nature. This was a fatal miscalculation. HTP is a high-maintenance propellant. It demands perfectly clean tanks, flawless welds, and constant vigilance. It is a chemical that punishes the slightest impurity or material failure with explosive decomposition. The Kursk's design was a paradox. It was a 21st century titan carrying a 1950s-era chemical liability. The indestructible double hull, the standoff armor, the 9 sealed compartments. All of it was designed to protect the crew from external threats. But the design, accepted and institutionalized, a volatile, internal threat. The faulty weld was merely the trigger. The HTP was the bomb. The moment that weld failed, the submarine's fate was sealed. The designers had built a fortress with a self-destruct mechanism, and on August 12, 2000, that mechanism was activated. The 118 men aboard were not the victims of an enemy attack, but of an engineering compromise, a high-stakes gamble on a chemical that, in the end, would not be tamed. The sea does not forgive engineering hubris. It is an environment that finds every flaw, every crack, every shortcut. The Kursk lies on the bottom, a 19,000-ton monument to a failed gamble, and a permanent reminder that the most dangerous threat to a machine can often be the very thing that was designed to make it powerful.